Hi, everyone. Thank you for joining us today. Welcome to the CARES Commercialization Talks. This series was started by Nick and Zhen, who will be joining us shortly. They thought it would be useful to have a space where CARES researchers who are planning to commercialize their work could connect and learn more from one another. And now it has also grown just outside of CARES, but we also include our CREATE colleagues and also our colleagues in Cambridge as well. So Dr. Nicholas Jose and Dr. Zhen Guo have both successfully created their own startup companies in Singapore and the UK. If this is your first time attending a talk and you're unfamiliar with CARES, we are the University of Cambridge's research center here at CREATE. We have been running since 2013, mainly doing work related to decarbonizing Singapore's chemical industry. Today, it is my pleasure to introduce Mr. Tony Dai, who is the director, founder, and inventor of the company called Epicam, based in Cambridge. Tony brings 40 years of experience in engine technology development to Epicam and has provided consultation to leading motor manufacturers such as FEV, Saab, Ford, and Perkins and consulting engineers Ricardo. Epicam itself is an advanced engine development company focused on bringing to market an engine providing post-carbon clean power. This began whilst Tony was lecturing at the University of Cambridge, where he is a senior member of Wolfson College. The Liquid Air Energy Storage and Regeneration Technology, or LAESAR for short, offers a means to provide renewable energy to the grid at times of peak loading and premium pricing using liquid air stored through our technology. It can also extract greenhouse gases from its atmospheric working fluid and simultaneously provide a substantial contribution to climate repair. So without further ado, I'll hand over the floor now to Tony to start his presentation.
Well, hello, everyone. I'm Tony Dai, Chief Technology Officer at Epicam Limited, and grateful to Olivia for the invitation to give this talk to you. I'm going to try to condense the rather long journey that has happened to bring Epicam to a point where we are able to address what I think are the two most crucial items on the global sustainability agenda. You probably are well familiar with the COP26 meeting, at which there was formed a newly founded council for longer duration energy storage. And the council came out with the clear and unambiguous statement that all power grids around the world must transition from current dependence on fossil carbon energy sources to full dependence on renewables. And it must be done quickly and in the next very few years. And that when it does happen, this will create a massive increase in the demand for energy storage. A power grid needs to have 10% of its capacity available in storage if it is to operate 24/7, 365 basis. And if you aggregate that around the world, for power grids around the world, you're looking at 1.5 to 2.5 terawatt hours of energy storage requirement. And there is no technology currently available which is able to address that issue. Secondly, only a couple of weeks ago, I think the IPCC, the Intergovernmental Panel for Climate Change, came out with a clear indication that they considered the accepted targets for net zero by most countries around the world were really very unambitious. In the UK, if we're to get to 2050 before we reach net zero, we will have probably an irreversible situation to handle, with the problem entirely in the atmosphere. So what they were saying is that it's essential that we begin extracting carbon dioxide directly from atmosphere in order to avoid these irreversible situations. So I find myself presently with my company owning a technology which I believe can address both of those two crucial issues. And it's quite an amazing situation, but one which I hope will indicate to you my feeling that this technology needs to be adequate funding available. So my story begins, well, I was born and brought up on a farm in Norfolk, small farm in Norfolk, 50 miles from here, where I'm at Cambridge now. And I studied agriculture at London University, Y College, and graduated, and then went overseas to Southern Africa for 4 years, and to teach. I'm mainly teaching agriculture, but also I took the opportunity to visit as many neighboring countries as possible. And one which caught my attention very soon was Swaziland. It's now Siswati. Right. And there I was introduced to a tractor project, and it was effectively Africa's first indigenously designed and built and manufactured tractor. The Tinkabi, that's the Siswati word for oxen. So it's like an iron oxen. And it was the brainchild of Alan Catterick, an engineer visiting from Yorkshire. And he quickly sized up the situation that Swaziland was in danger of massive soil erosion, mainly due to the preponderance of oxen. And so he thought what we could do for a technology that would supersede the oxen team was this machine, which was produced and manufactured and supplied throughout the country with a small range of oxen type implements, plow, seeder, and so on. But it was also very adaptable. As you can see, he realized that there was no point in raising the productivity of small farms in this situation unless the additional output could be marketed. So it's a transport system. And as you can see, soon also became a taxi, local taxi service. It also was able to be adaptable for special applications like crop spraying of cotton, which introduced the opportunity to farmers to grow a crop they had not experienced before. And as you can see, also, it was readily available for other members of the family to operate and become familiar with. What occurred to me was that this certainly was potentially a technology which could be replicated throughout the third world. And then I thought, well, what are the implications if we want not just millions, but probably billions of these? And then my attention focused on the engine. There it is. You can see, can you see my pointer? Olivia, can you see the pointer? Yes, okay. That's the two-cylinder air-cooled diesel engine from Kirloskar in India. It produces about 15 kilowatts, 15, 16 kilowatts. But what I thought of it at the time was, well, it's a massive lump of steel and technology. Is there possibly a simpler way in which you could produce 15 kilowatts to power mechanization of small farms throughout the third world? And I started thinking in terms of three-dimensional shapes. And what I came up with, you may be able to see on this screen, through the transparent wall, you can see two rotors, a two-lobed rotor on the left and a three-pocketed rotor on the right, so that the lobes and the pockets can interact. And the two shafts are geared together with timing gears that preserve the correct angular relationship between them. And what I will show you now is the means by which compression and expansion are achieved with this type of device. It's a complete compression cycle. And here's the second one now starting to operate, okay? You have to imagine these rotors are mounted in the housing with close-fitting walls at front and rear, but not actually making contact with those walls. So the rotors are able to rotate without making contact, and therefore the compression takes place without any internal mechanical friction. So that demonstrates compression. Of course, I can't show you the porting that allows the delivery of the compressed air in this case, as it would be to whatever receiver is available, and how the air would get into the housing which houses both the rotors. So what they're doing really is just swimming in working fluid. If I can, I might be able to rotate it backwards so you can see the effect of expansion. Let's see if we can do that. No, we're not able to do that. Anyway, if you can imagine it, the process is exactly the reverse of what you've just seen. That as the rotors counter-rotate, a small new transient chamber is formed, which expands as the rotors counter-rotate. And one can look at a very high expansion ratio. We think in terms of 400 to 1 for quite a small size of machine. Can we just go back one?
Yep.
Oh,
yep, no problem.
Right. At this stage, this was just a concept, and I realized that you could have two devices, one compressor and one expander with connection on the same shafts, put a combustion system between the two, and you might have you would have an internal combustion engine with potentially world-beating characteristics. So at that point, I realized I could do nothing because I had no funding and I had no patent protection. So I couldn't even talk to anybody about this. So what I then did was to turn my attention to the auto industry. I thought if I could learn something about how the auto industry works and how it might be possible to introduce technology into it. Okay, so I'd like to move on now. Could we move to the next screen? Okay, whoops. What I did was I got a Ford Anglia car, heavily modified the engine to run on 2 cylinders instead of 4, and used the 2 center cylinders for double expansion, and to recover the heat from the exhaust and introduce it as superheated water. And I took this car down to my friend in Wiltshire, where I'd done my practical work on the farm, and he gave it a test on the road, came back and said, yes, you know what you're talking about, I'll fund you. And the result was that I then had a dynamometer, an engine dynamometer, so I could do engine testing, and some electronic equipment to monitor cylinder pressures. The idea of recapturing the exhaust heat was not easy to actually turn into practical use. But I then discovered a a process that was happening in conventional gasoline-powered engines known as intercyclic combustion variation. You might think you've probably ridden in a petrol engine car, and if you're considering driving along at 60 miles an hour on a level road, every time pistons going up and down, every other time you're going to get a combustion event, and the pressure will shoot up to a maximum and come down again. And you might think, well, they're all exactly the same because they sound all the same. Yes, they do. But the reality is that they're quite different. The peak pressure on each successive cycle is quite different, and indicates that each combustion event in a petrol engine is unique. And the variation from cycle to cycle is what causes this problem, and it's due to turbulence. The turbulence in the cylinder, which then affects the rate at which the flame propagation takes place. And I realized that the turbulence is set up at the throat of the intake valve. So here you see 4 intake valves. This one on the right is the standard intake valve. I don't know why this isn't showing on my screen. Is it showing on your screen? Yes? Okay. And then you have 3 valves, which I have modified by introducing a turbulence controlling grid on the surface of the upstream surface of the valve. So it processes the flow as it goes into the cylinder. And this establishes uniform small-scale turbulence, which aids combustion and control of combustion. So what you see on the next slide, which I can't, oh, here we are. Can you see this one? Yes. The top, well, there are 2 traces of cylinder pressure from engine operating under test on the rig. And the top one is cylinder number 4, which has the modified grid valve. Compare that with cylinder number 1, which has the normal intake valve, and you see how the peak pressure varies enormously from cycle to cycle. And engineers had been trying to fit functions to this to define, well, what is it that's causing it? There must be, no, there's no function at all that fits. It's a completely random walk. And that's because it's caused by turbulence. And if you don't control the turbulence, then you don't have very good control of combustion. What I then was able to do was to work with Ricardo's, the consulting engineers to the auto industry. They liked this and set up a test. They bought a car, drove it for 1,000 miles, put it through the test rig, and threw the book at it. And they said, right, we've got everything that we need to know about the performance of this engine. Come and modify, put your modified cylinder head on it, and we rerun it. And when they reran it, they said at the end, well, you've got 20% reduction in fuel consumption. You've lost some power, but it still has the same power as the 2-liter version of this 2.5-liter engine. So it's virtually adaptable. And you've got emissions like we've never seen before. And we were able to show that it's possible to lean the fuel-air mixture to a point where there's no further nitrogen oxide emissions formed. But probably the most important thing that happened as a result of this development was that I met my first real mentor, Dr. Bob Fielden, who completed his engineering at Cambridge in the early part of the Second World War, was then drafted to Power Jets to work with Frank Whittle on the first jet engine. And he subsequently had an illustrious career throughout in the aero industry as director of engineering at Ruston's at Lincoln, and designed complete ranges of gas turbine engines. when he finally retired, became a consultant, and he saw this this work of mine, and he was very attracted, and he said he liked the look of the grid valve. He said it seems to be an elegant solution to what's a rather intractable problem. And so he said he would work with me, and we went together to the Department of Industry, who said at that time, we're talking mid-80s, mid-1980s, Germany has a problem. They say the forests are dying, and it's because the Mercedes are going at 200 kilometers an hour down the autobahns and pouring out nitrogen oxides, which is coming back as acid rain and affecting the forests. They were actually wrong about that. That wasn't what was causing the problem with the trees. Nevertheless, they were concerned about the technology being used in the auto engine industry. So they liked the idea of a possible 20% reduction in fuel consumption and no nitrogen oxide emissions. And they said then, well, how long is it likely to take? And the Department of Industry said, well, you're looking at around 2 years. And they said, what? 2 years? The forests are dying. We must have a solution. We must have it now. The Americans have it, and it's called three-way catalytic converter. And that was the way the decision was left. I realized that this might be, well, it was the end of my work on lean burn combustion. We can contemplate now that ever since the mid-1980s, all petrol engine cars have been using 20% more fuel than they ever needed to, and have been fitted with expensive catalytic converters, which they also didn't need. However, I realized that it might also end my association with Bob Fielden. So I took him into my confidence, made a drawing on the back of an envelope of the paired rotors, which you've seen. And he liked that very much, and said he would help me as long as he could. And he did, until he died, unfortunately. So how I can move on, I don't know. Oh yes. What we did was first to build a compressor, and this was able to attract the attention of two successful entrepreneurs from Belgium, Karel Bos and Ton Coat, and they funded the development with eventually £2.5 million to build an engine. They wanted to see a new IC engine, and that is what we did. We built the engine. I can't get it to move on. Can we move it on? Yeah, whoops, too far. That's it. Here is the engine which we built, and it's on its test rig in our facility, which was then a small unit on an industrial estate. And you see that within this casing here, you have the gear wheels at this end, which time the rotors. The compressor is on this side. The combustion system is in the center, and there's access to the spark plugs on the other side. You can't see that. And behind is the expander with the exhaust pipe coming out here. And what's going on inside here is shown on the next slide. Now, can we animate this one? Yes, we can. And now you're looking at the compressor end. So the compressor rotors are delivering compressed air into the chamber, which is the brown cylinder in the center there between the two sets of rotors. And the expansion takes place in the expansion rotors here. And you'll see they're twice as long as the compression rotors, because when you combust a fuel air mixture, it wants to expand by twice its original volume. Right. So let's not go on. Can we go back? Right, let's just hold it there for a moment. What we were able to do then was to demonstrate this engine to Rolls-Royce and General Electric. we're now talking in 2003. We started contact with those two organizations, and they were at first ecstatic. I mean, we had to kind of scrape them off the ceilings and get their feet on the floor to start sensible discussions. And the discussions and negotiations then went on for a year. And they were saying, look, Tony, you've shown us the most efficient and effective way to convert fuel energy to shaft power that we have yet seen. And they didn't have any doubt about that. But at the end of a year of discussions, they were both saying the same thing to me, which was like, Tony, nobody but nobody is going to build your engine. And it's not because we don't believe it. It does what it says on the can. It will achieve what you're looking for. But it would also destroy Rolls-Royce. And I don't know what it would do to General Electric. What they then said was, look, you've got the best way to compress gases, yeah, including air, of course. Air is a gas, yes. To compress and expand, you have the best way of doing it, with no internal friction, mechanical friction, and opportunity for very efficient compression and expansion. What you've got to do then is to look for an application where you don't immediately get into industrial disruption on a massive scale. So I worked for a few years with Valeo, the French company. We designed a compressor for supercharging their downsized petrol engine, which very nearly went into production. But just as it was about to do that, I received the invitation, this was then 2014, to visit Highview Power. Highview Power was a spin-out from Leeds University, where there was a cryogenics laboratory, and they had been experimenting with liquid air and realized that it takes a lot of energy to make liquid air. So therefore, it could be used as an energy storage medium. And their first plant was demonstrating the process on an industrial estate at Slough. And I was invited down to visit, and when I saw it, I very quickly realized this is the opportunity that we have. Highview had decided to commercialize this technology and use for compression and expansion, and it is really only compression and expansion of air, turbo machinery, which had the advantage for them that they realized they were introducing to industry a new technology, and one with which industrialists were pretty well unfamiliar. So the first question that would be arising from a prospective operator is, look, well, how do we know that your technology is going to last the 25 or 30 years that will justify the expenditure of many millions of pounds to implement it? And they were able to say, well, we use turbo machinery, which has a track record in the aero industry and in energy industry, which shows that it has that kind of longevity. No problem. From our point of view, it also placed some limitations on the technology for Highview, i.e., it limits the efficiency, because turbo machinery is not able to achieve such high efficiency or high pressure ratios as are possible with displacement technology, displacement compression and ignition and expansion rather. Also it limits their scalability. Turbo machinery has to be large. It cannot be scaled down. Our technology can be scaled to any size that's required. Let's see if we can move on. So what we had to do was to first design a system for delivering liquid air. And the way we did it was, as you've seen on the screen. Can you see this? Yes, carries. Okay. So we have power input on the left-hand side of the screen with four electric motors driving power lines, 4 power lines, each of them having a direct drive to successively 3 compressors. The first stage compressor takes the air up to about 4.5 bar. It then goes through a heat exchanger because we want to recover the heat. The heat there at about 450 degrees K. So the heat is stored, and the charge then goes to the second stage compressor, which will also by about up by 4 times to 20 bar. Again, heat exchange, and third stage, another 4 times, takes you up to 80 bar. So the object is to get compression of air up to 80 bar. And then what you've to realize is that the lower 3 power lines are required in order to provide the cooling for the fourth charge, which is in the number 1 power line. So what you do is to put the air at 80 bar and ambient temperature through an expander down to ambient pressure. The cooling is subsequently through heat exchangers submitted to the air which is compressed from number 1 power line. So at the end of this stage, we have from number 1 power line, we have air at 80 bar pressure cooled to a temperature of 105 degrees K. And if you then put that through a final stage expander to ambient pressure, it will largely liquefy, and leaving only a small proportion which is easily recycled through the system. So we have a basic liquefaction system, and we then go on to expand it. And I have to apologize for the rudimentary nature of this diagram, but at least it just illustrates the elements. So we have 2 energy storage elements. One is the cold one at 75 degrees K, and the other is the hot one at about 450 degrees K. From the cold liquid air in the reservoir is introduced into a small bore pipe, which is assisted with a high pressure pump through heat exchangers to an injector in the expansion engine. So what it means is that as the liquid air passes through this system, its temperature rises, but it tries to boil, but of course it can't, because the end of the pipe is closed by the injector, and so its pressure rises. And as its pressure rises to about 170, or about 30 bar pressure and 170 degrees K, it will then phase change to gas. So it then becomes a supercritical gas with the same density as the liquid air from which it was derived. And it's that supercritical gas which is then injected into the expansion rotors of the rotary engine, the new rotary expander engine. That then produces shaft power, which is used to drive a generator and produce the power which is then supplied back to the grid. So that gives you a sort of summary of the system that we proposed. Can we go on to the next slide? Oh, well, here you see a prototype engine with its rotors, and it's an expansion engine with injectors on the rear side. That's shown on the next slide. The injectors are in here, and they're delivering this supercritical air, ideally, into the rotors and producing power. We weren't, of course, able to build the liquefaction system in advance, so we just used nitrogen gas to prove the concept. So now you see the whole system really is 3 modules: compression module, in which air is reduced to its minimum volume, maximum density as liquid. It's stored, the heat is extracted for storage also, and then the stored energy can be recombined in a heat engine, as you've seen, to regenerate the electricity. We have carried out an exercise in cooperation with a high-level team at Imperial College. So they have studied this complete system, and they have constructed a thermodynamic model for the system, and they have concluded that when built and connected to a power grid, the system will deliver energy storage to the grid with a round-trip efficiency of approximately 68%. Now, when I saw that, of course, if it's proven in practice that is possible and it can be done, then it puts the technology into a really leading position as a contender to provide the main energy storage requirement to meet the challenge set by the Council for Longer Duration Energy Storage for application on power grids around the world. The next consideration was, well, if that were to happen, or when it does, we will be seeing this technology, this LAESAR technology, processing teratons of air. But because we're taking air itself down to a temperature reduction of about 200 degrees centigrade, we're going through the points where it is possible to extract the carbon dioxide and methane greenhouse gases in the air. So the next question that I then asked myself was, well, if that were to happen, how much carbon dioxide could be extracted globally? And what I considered was that when the manufacturers of wind turbines start to look at this, they might say, well, do we really need to go through a stage of conversion of wind energy directly to electricity? Why don't we use the wind energy from the turbine to drive the liquefaction unit? And then the unit is then storing in a reservoir energy, both cold and hot, which can be withdrawn and directly and converted back to power to drive the grid, to power the whole grid. And this would simplify the supply and demand equalization on power grids. So it makes that problem much simpler, and it would then mean that the whole of wind power would be being used to also extract carbon dioxide from the atmosphere. And in simple calculations, it looks to me like within a very few years, we would be reaching the 10 gigatons per year target of the IPCC, which they have said is necessary if we are to repair Earth's climate. And that's really where I think I would like to leave it. You can go on. There's a couple more slides, I think, but that's it. Now, I'm hoping that I've left enough time. If there are anybody who wants to ask questions that in order to improve the clarity of the presentation in any way. Can I open it for questions?
Yep, we can open up for questions. So as I've mentioned in the chat box, feel free to post straight on the chat box, or if you want to direct message it to me, I can read it out as well. Maybe to start off, I did have a question as I was listening to your presentation. So towards the end, you mentioned the whole carbon capture process. That was something that was really exciting to look forward to. But I guess on the other hand, how far away do you see this technology for use in small scale settings such as households? If we wanted to start small, or is your idea that we go big, or do we start small in smaller settings first?
Well, that's a very good question, Olivia, because this technology is completely scalable. So you could, for example, develop a system which would provide energy storage for a household, a single household, or maybe a small group of households, and it would be entirely effective. On the other hand, you can scale it right up to meet the energy storage demand on a continental scale grid. So the technology is completely scalable, and really the answer to your question will be determined by market forces. I think what I'm trying to communicate here today is that I believe this technology is worthy of full funding. And if that is available, then we will see which way we can develop it. It's also quite possible that as a result of developing first in energy storage, we will find that the engine itself becomes very useful. It's clear from our modeling indications that it will have a far higher power density than is possible with internal combustion engines. So it could have applications in the transport sector and elsewhere.
Yeah, that's amazing. And yeah, I think the fact that it's completely scalable, yeah, like you said, it could enter so many different industries and fields that, yeah, so many utilizations there.
Yeah, thank you.
Yeah. All right. Anyone else have any questions they want to add?
Yeah, I've got one. Just first, thanks, Tony, for the talk. And for talking about the potential for your technology, especially in carbon capture. I guess this is a sort of general one about transitioning research into more commercial application, and I think this is sort of why we hold the series, right, to help researchers learn about these different stories, right,
Yeah.
to basically commercialize their technology. So do you have any sort of tips, I guess, in the area of sustainability and commercializing research in terms of how to really get things off for researchers themselves?
That again is an extremely good question. The story I've tried to present to you today has spanned my experience over several decades, and I'm not convinced that there is any rational process that will automatically lead to the correct investment being made in any particular technology. It's a risk game, and you just don't know what's around the next corner. There could be a meeting with an individual who's fired up with this and will make heaven and earth move, but it may never happen. One just does not know, and you live in hope. And I think that's the important thing. That if it's potentially possible to be done, then somebody sooner or later is going to be sufficiently inspired to say, look, we have to do this.
Thank you. Yeah, thank you. And I guess, I mean, you're involved with the university as well. Do you think that, working with universities is one way to sort of help generate these technologies and, get them to more mature states? So like, what's your interaction with universities in your research and commercialization?
I think my experience confirms me in the belief that I did right by leaving the university. when I first started, of course, my university experience gave me the opportunity to learn computing. I learned from scratch. I learned Fortran and used the computer, and then realized, oh my goodness, what a great tool this is. We could use it to, for example, model the cycle of an engine. But then, of course, I realized that there potentially was an issue that the university would say, well, hang on, look, you're using our system to develop your technology. That's not right. That belongs to us. But there was, in the end, no argument about it, because my contract was with the Department of Land Economy, and there wasn't any way by which the department could interpret my contract as meaning that I was responsible and required to develop engine technology. So but I think I had good experience in land economy. And when I left in 1980, and I worked with UNIDO in Vienna for a year, I realized that it was good to have good connection with industry, and I've benefited from that also ever since. So I think that if you're an academic and you're stuck with your ideas, then the thing to do is get out into the industrial world and see where they will fit.
Great, thank you.
Yeah, thank you. Those are really nice, good words for anyone here looking to commercialize their scientific research. All right. Is there anyone else who would like to add a last wording? Okay, if not, I think, well, yeah, Tony, we can say thank you very much for your time today and for your presentation. As mentioned, this talk is recorded, so I'll be uploading it soon, and I'll share it with everyone who attended today. And yep, Tony, you can also, I guess, share that on with others as well. But
Okay.
yeah, all right. Yeah, thank you very much, everyone, for your time.
Thank you very much, Olivia.
Thank you.